This is the introduction to WAN optimization traffic. We're going to take a look at using Wireshark to assess the effectiveness of your WAN op features and deployment. So moving right along, here we go. So this session is actually an update to the one I did, the virtual US session that I did last year. And due to time constraints for today's session, I'm going to skip some of the background and intro material. I'll also move through some rather quickly so that we can get straight into Wireshark. But you can find the additional background and the key concepts in the US virtual session. And the links to that session are here on this slide, SharkFest Virtual, wireshark.org. And the link to the YouTube session. So a little bit about me. I've been a SharkFest instructor since 2017, been heavily involved in performance engineering since the early 80s, and protocol analysis in particular since the early 90s. I've been with professional services at OpNet and Riverbed since 2005, and I think for those of you who have seen my session before, you know that I love the mystery of a complicated performance issue. And you also know that I shaved off my beard in 2003. So no more beard. So why did I think this session might be interesting? Well, it's because WAN op technologies in general will modify or enhance what you might consider to be normal protocol behavior. And you're going to be seeing some protocol behavior in Wireshark that might look confusing and questionable. I know it did for me the first time I had a look, which is why I was really thinking about this session. And, you know, the more background that you have, the more effective you will be interpreting Wireshark to evaluate your WAN op deployment, you know, whether you want to make sure it's configured properly or you're doing a proof of concept and you want to make sure it's providing the benefits that you were expecting. So what's also interesting is some of the behavior that we're going to look at is very similar to other tunneling and proxy technologies. So you will, as we go through this content, you will gain knowledge that will help you in a variety of special technology situations. So that's why I put the session together. Here's our agenda. The first two bullets will go pretty quickly, why WAN op, and an overview of features. It really will just be a subset. I would ask that you take a look at the virtual US session from last year to see the full landscape of features. But so after that, we're going to jump into Wireshark samples and look at some analysis examples, and then we'll wrap up with Q&A. So here it is. It's time to get started. So why WAN optimization? Well, it really comes down to we're trying to provide some benefits to the organization, improving user productivity through faster response times, and also reducing WAN bandwidth usage. That was one of the early drivers for WAN optimization. But there's a new one around reducing cloud egress costs. So for those clouds that are charging, you know, your rate, your cost is based on how much data leaves that cloud, there's some opportunity to reduce that amount of traffic and therefore reduce the cost. So those are the high level benefits. Let's look at some concepts to level set some terminology and do some baselining. So as anyone who's done any performance analysis knows, you know, application performance is heavily reliant on network performance, particularly around latency, end-to-end network health, bandwidth, congestion. All of those things can lead to poor application performance, and typically as I suspect everyone here would say, the network is the first to get blamed. While, it can also be other factors, certainly like, server utilization or application coding or other data related factors that are messing up the application. For our discussion today, we're going to be focusing on the network. And in particular, we're going to focus on latency. And I want to distinguish between latency and a term I'm going to introduce in a second. And I'd like for you to think of latency as that measure of propagation delay across the network. So it's really the physics of getting the signal across a particular distance and time. And generally, the higher the distance, higher the latency, the worse the performance will be. And we'll dive into that in just a minute as well. So the closer you are to the server, you might say, wow, the network is fast. The farther away, you're probably not going to say that. And it doesn't matter how much bandwidth you provide, it's the distance that's going to provide the challenge. And we're going to spend a lot of today's session is around that distance effect. So separate from latency, and again, I'd like you to think of latency as the speed of light propagation delay across a particular distance. You can't do anything about that propagation delay. So the round trip time then is, think of that as the time required to send packets between two hosts, A to B, and then back to B to A. Think of round trip time as including latency, speed of light delay, but also congestion and protocol delay as well. And again, more or faster bandwidth is not going to improve latency. So we have to find different ways of addressing latency, and that's what we're going to be covering in today's session. So let's get back to, there we go. So there's a couple of Wireshark metrics that are very relevant to latency and round trip time. So the first one is TCP analysis.initial_RTT, usually represented as small I, capital RTT, and it's a static value for the life of a connection, and it's a measure of from SYN to SYN-ACK, plus there's an X factor that I haven't really found a good explanation for yet. Doesn't mean it doesn't exist, I just haven't found a good one. So that's the first one we're going to be looking at. The next one is ACK round trip time. So how long does it take to ACK a particular TCP segment? And then the third one is ACKs_frame. What is the particular frame that's being acknowledged? So we'll get some sense of how long did it take to set up the connection, initial RTT, and then throughout the life of the connection, what can we learn about changes in round trip time using time to ACK and ACK for frame. So here's an example decode. I'm going to try to zoom in a little bit to that, make it a little, hopefully a little easier to see. Whoops, come back. There we go. So here we can see a three-way handshake, SYN, SYN-ACK, ACK, and you can see that there's an RTT value that shows up on the SYN-ACK, and again, that's being calculated by Wireshark. And notice it's also a little bit higher than the actual SYN-ACK delta time, and that's the X factor that at the moment I don't have a great explanation for. So I was thinking it might be, if we factor in the third part of the handshake with the ACK coming back, and that math kind of works a little bit just looking at these numbers. So it might actually be the total observed of SYN, ACK, and ACK. But the key is to be aware of it, and it's going to provide some value in our analysis. The next one is what I usually label as round trip time to ACK and ACK4. And in this case, I'm going to zoom in here as well. You can see now the initial round trip time column as well as round trip time to ACK and ACK4. So ACK4 is really helpful. It tells you the packet that's being ACKed, and then the round trip time to get that ACK back from the distant end. So very useful numbers. And I have a question on the slide, which is what is the round trip time to ACK the client hello message? So here's our client hello message being highlighted on the screen. And you can see if I zoom in a little bit, I'm going to assume that zooming in is helpful. So we'll continue to do that. So the round trip time to ACK the particular client hello was 83 milliseconds and some change. So there we go, 83 milliseconds and some change. So initial RTT, RTT to ACK, ACK4, those are some very helpful measures of round trip time, which does include latency. And I want to introduce a key concept, which there's not currently a metric in Wireshark specifically for it, but that concept is an application turn. And an application turn is the pair of a request message followed by the response message. So the two together, the request going out, the response going back, is one turn. The request message could be multiple packets. If you think of a post, HTTP post with a lot of payload, that could indeed be multiple packets. And the response that comes back might only be one packet, or it could be multiple, but it's one turn. And the key is that for every turn you have, the duration is at least one round trip time. There's no way around it. And 10, so if we just take an example, 10 turns at 100 milliseconds of round trip time is going to cost you 1 second of response time or duration. So a couple of really quick examples. In terms of HTTP, the request would be a GET. The response would be some HTTP code response, a 200, a 301, 304, whatever the response is, hopefully not a 500. So that's an example of a turn in HTTP. In SMB, an example would be maybe a read command, in this case, reading the 16 KB block at file offset 0. That's the request heading to the server. Then there's a turn and the response comes back with the requested data block, in this case, potentially 16K if there's that much data. And of course, that would be multiple packets. But at the application layer, it's one turn. Last example, SQL, pretty straightforward. There's a select command from a database client to the database, and there's an application turn. The response, the status of the query comes back along with the rows from the database, assuming there are rows. So application turns are a key concept. And there's one more useful metric that I want to put up on the screen, and it reflects that some of the decodes, not all of them, but some of the decodes are able to measure and report on the delta between the request and the actual response in terms of a time delta. So I'm just going to zoom into this a little bit as well. So here we have an HTTP GET and a OK that came back. And in this column, time since request, the field is actually http.time. So with SMB, it'll have a different field name, but it's the same concept. And the idea is it's giving you a measure of how much time was there between the request and the response. So another useful metric, we've got 4 under our belt now. So let's move on to talk about transport layer and TCP. Is it sensitive to latency? Does it have a concept of turns as well? And if you think about congestion window mechanisms like slow start, delayed ACK, retransmits, fast retransmits, things like that, there is a round trip time penalty for some of these mechanisms. So, so the answer is yes, it is sensitive to latency, and the higher the latency could impact your TCP transport performance as well. And that kind of leads us into a key point from this entire session. And you know, my hope is that if you leave here with only one key point from our time together today, I hope it's going to be this key point, and that is latency times turn rate. So we've introduced what a turn is. A turn rate is just, let's say, the number of turns per second or some interval. So latency times turn rate equals user pain. The higher the latency or the higher the turn rate, the higher the user pain, and therefore complaints from users, and it's always the network, so we get dragged in to help figure it out. If you can reduce the turn rate, you can reduce user pain. And if you can reduce latency somehow, you can reduce user pain. So anything you can do to improve user experience is generally a good thing. And when we looked at our key benefits at the beginning of the session around WAN optimization, it's improving user performance, reducing bandwidth. These things would hit that bullet of improving user performance. So quick review. Again, we're going to move quickly so we can get to some Wireshark samples. Challenges to user performance: not enough bandwidth, transport protocol chattiness, application protocol inefficiencies, and latency is what drives those top 2 crazy. And ultimately, you have to solve all 3 to see performance benefits. If you solve for bandwidth, but you don't solve for latency, it's not going to necessarily create an improvement for the users. All right, so that's our super high level background around some of the protocol concepts. And let's move now into a few slides on Steelhead features overview. So first off, some of the key features are around transport optimization, TCP proxying and spoofing, some super intelligent caching, compression, dedupe, WAN connection pooling so that connections are already open between 2 endpoints. You don't have to suffer through connection setup time, let's say from Singapore to London. The connections are already open. Overriding some TCP options at the 3-way handshake. We'll see some examples of that. There's also some enhanced packet loss recovery mechanisms. So regardless of what the 2 endpoints are able to do in terms of packet loss recovery and retransmissions, the WAN up devices have their own enhanced capabilities to make packet loss less of an issue. And then finally, being able to detect super high latency like satellite links and switching to some optimal protocols specifically for super high latency links. There's also some features around application protocols. So we talked about TCP and transport, but there's also some very specific optimizations for specific protocols, like being able to prefetch or change some behaviors at the negotiated protocol settings. Like, for example, with HTTP, if one end says close the connection at the end of this request, we're able to override that to say, actually keep the connection open. We don't want the overhead of opening new connections for every single request. So prefetch, read ahead, caching, and then some other quality of service, policy-based routing, some other capabilities. In a nutshell, because we don't have time to go into all of these in this session, in a nutshell, there's some common themes to all of those optimizations. And those themes are, guess what? Reducing turns, reducing payload. Remember, if we can reduce turns, we can improve performance. So ultimately, if we do those things, we can reduce user pain, which is really the mission, reduce user pain. So that's it for our background stuff. We're about 20 minutes into the session, and we're going to now move into drilling into some Wireshark analysis and timing samples. Speaking of timing samples, ignore the little stopwatch in the top left-hand corner of this slide, and it may show up in some others. I meant to take those out before the session, so they're not really relevant to today's session. So we're going to look at two different scenarios. The first scenario is from a virtual lab environment where we have a couple of virtual steelheads simulating a branch and a data center. We're going to look at enhanced auto discovery, and we're going to look at some transport optimization features in action. And then we're going to jump to scenario number 2, where we're going to look at a version of Steelhead that's running on my laptop. It has the name Client Accelerator, and it's going to be connecting to a Steelhead in Office 365 known as SAS Accelerator. And I'll be looking at some controlled tests where we're going to look at transport optimization and improved response times. So let's get started on scenario 1. So a little background, it's from our training lab environment. All the components are from our training lab environment. It's virtual everything. So steelheads are virtual. The client hosts the server, the WAN is virtual, the latency injection is all virtual. And you know, I just want to make a comment. Virtualized components are great when you're doing functional testing. When you're doing performance testing, they can throw you off a little bit. And you know, I'm grateful that we had an environment where we could spin things up and do some controlled tests. But at the end of the day, we have to just remind ourselves that virtual everything. So when the Steelhead is doing its processing, it's subject to, hey, is ESX going to give me the cycles I need to do my work or not? So virtual everything, and we're going to explore something called enhanced auto discovery, and then we're going to look at some transport level optimization. And the reason I picked these two is, you know, one of the goals for this session is to share with you some things that you might see in Wireshark that maybe look a little strange. And that's what I want you to be able to walk away with. In addition to the key point from a few slides ago of latency times turn rate equals pain. So, but I do want you to be able to recognize things in Wireshark that are relevant to, again, WAN optimization in general, Steelhead in particular, and other kind of proxying type and caching type technologies. So here's a little bit about our topology. We've got a client that pretends to be in a branch. We've got a Steelhead that pretends to be in a branch. We call that the client Steelhead. We've got a simulated wide area network of a 1.5 meg and 96 milliseconds of latency between the two sites. Then we have a server-side Steelhead in the data center on the right-hand side, and then our web server. And as part of pulling these captures, we're opening the web server, opening a folder, pulling down some high-res images to generate some traffic. And I've got 4 capture files, which I'll upload with the presentation after the session, in case you want to look at these after, you know, post seminar. So one of the things we're going to look at is auto discovery. It does look a little bit funny when you're looking at the captures, so I wanted to make sure we talked about this. It's initiated by the client-side Steelhead. the goal is to discover, are there any other steelheads in the path that are close to my endpoint server? And if there are other steelheads in the path close to my endpoint server, let's set up a peering relationship and optimize the traffic. And the endpoint client, the endpoint server are totally oblivious to this happening in the middle of the path. So it's totally transparent. In terms of a bounce chart of what does that look like, we can see starting from the left, the client sends in the SYN, the client steelhead sees that SYN, forwards it on up the path. The first steelhead doesn't really know what's in the path on the way to the server. So this begins our discovery. And we're going to look at the details of the TCP options in just a second of what's in those SYN packets and what's in the SYN ACK packets coming back. So the SYN ultimately gets passed up the stream towards the server. In this case, we're going to hit a second steelhead. It's going to pass on a SYN to whatever is upstream. Steelhead number 2 doesn't assume that there's not a steelhead number 3, because there could be. Onward towards the server gets it, says, hey, look, a SYN packet, let me do a SYN ACK. And we'll complete the 3-way handshake with the server side steelhead, in this case, steelhead number 2. The 2 steelheads start to negotiate some control mechanisms and settings, and then eventually steelhead 1 will complete the 3-way handshake with the client. And we're gonna look at that in some detail coming up here. So let's be on the lookout for some of the unique behavior. We're going to see some new decode labels that you may not have seen before. We'll talk about those. You're going to see a SYN ACK retransmission. We'll talk about that. You're going to see that the initial round trip time is higher than what you might expect. We'll explain that. And we're going to see some TCP options being modified along the path. We'll take a look at that. So I've put together on this slide the 3-way handshake as seen from each of the 4 capture points: the LAN side of the client steelhead, the WAN side of the client steelhead, and then the WAN side of the server steelhead and the LAN side of the server steelhead, so that we can see all of the interaction that's taking place along the path. And in a minute, we're going to take a look at the journey of the SYN packet across all the interfaces, and then we're going to talk about that a little bit, and then we'll look at the journey of the SYN ACK. So here begins our journey of the SYN packet. So we're going to start at the far left-hand side where the client is, and these TCP options are coming from the LAN 0 interface of the client steelhead. So this represents really what we're seeing from the client. And as you can see, if I drill in a little bit to that, you can see the client says, hey, maximum segment size, 1460, that looks right. Window scaling of 8, that looks pretty interesting. And yes, I'm happy to do SACK with you. So that's what the client asked for. And next in our journey, if we take a look at what comes out of the WAN interface. So now in the WAN interface, let's see if I can do this. There we go. In the WAN interface, now we've still got the 1460. We've got everything that the client provided, plus we've added something called a riverbed probe query. And we're saying, hey, my name is client steelhead 10.1.120.21. Just in case there are any other steelheads on the way to the server, I want you to know, hey, I'm on the client side. This is my IP address, and maybe we can set up some optimization if that makes sense for the journey. So let's look at what happens next. Now, this particular capture from this WAN 0 interface turns out to be the exact same. I should have left this off. Apologies for that. And there wasn't time for me to do it, to undo this. So you're going to see all 4 captures showing up in these slides. Just recognize that what we see on this WAN interface is the same as what we saw leave the other side. So let's see now, what does the server steelhead present to the web server? So that's going to be here, and we'll zoom into that a little bit. So now we've got a couple of changes. Notice we've got timestamp option now. So the server side steelhead decided to turn that feature on so that it could have better understanding of what might be upstream. And we also changed the window scaling. So that was a decision made by the steelhead to perhaps reduce the belief being that, hey, I'm closer to the server. We don't need window scaling so high. I don't want to get overrun, but I want to be able to respond at land speed. So I don't really need such a high window scaling. And we can see that just in case there's yet another steelhead upstream, we've preserved the original client steelhead IP with the notion that this is a probe query request. So let's take a look now at some of the decodes. So this was all TCP options. Let's take a look now at some of the decodes. So here we are with the 4 captures overlaid on top of one another. And I want to zoom in on that, if it'll let me. Zoom in is being a little tricky. So here we are at the client side steelhead at the top. Everything looks pretty normal, and we see some HTTP traffic as we would expect, given that this is an HTTP test. And then if we go down a little bit, we see the client side steelhead now has an S+, and then we see a SYN with a ++, and then we see a retransmission of a SYN with a plus. So, or sorry, SA+. So we have a SYN, an S+, SA++, SA++, and an SA+ as a retransmission. And we want to understand what the heck that is all about. And I have a slide, next slide will explain it. The server side WAN, steelhead WAN interface is the same capture. Again, it didn't really need 4 captures for this example. I could have gotten away with 3. And then on the LAN side, we see the S+*, which is basically saying, hey, I've been through, the client initiated, I've been through a second steelhead, just in case there's a third steelhead in the path. Want you to know that we've gone through 2 steelheads already, trying to figure out who's going to peer with who. And in this case, there's only the 2 of them, and we'll see them peering in just a minute. But notice that the SYN from the server, so the server just ignores all these TCP options that it doesn't care about. The SYN from the server doesn't have any special flags. So let's take a look at what these, there we go, at what these special flags mean. So they're basically, it's the S+ is a probe. Hey, any steelheads in the path. SA+ is a probe response. S+ asterisk, hey, I'd like to do auto peering if there's another steelhead upstream, more than 2 in the path. And then there's some other special purpose interesting decodes that you'll see. And this is in the standard Wireshark. This is not any special version of Wireshark. It's the standard version of Wireshark. So some questions you might have about all of this. So why does the server-side SYN, server steelhead SYN, have the +*? We just talked about that in the last slide. Why don't we see any HTTP traffic on the WAN interface captures? And we'll talk a little bit more about that in a second, but the net of it is we have a connection pool between the two steelheads, and the traffic that's coming from the two endpoints is going across that connection pool, not as HTTP traffic, but as optimized traffic in special formats. Kind of, you could think of it as a tunneling protocol between the two steelheads. It's encrypted, it's tunneled, it doesn't show up as HTTP. So another question, why did the server steelhead change the scaling factor? Well, I can't tell you exactly why, I just have an opinion. And the opinion being, hey, if the thing I'm talking to is locally LAN attached, I don't really need a scaling factor of 8. So let's ratchet it down so that we don't kind of get overrun with too much traffic at once. Why did we introduce TCP timestamps? Again, I think it's because, hey, if I have the timestamps, I can make some good decisions about throttling, not throttling, changing receive window sizes, etc. It helps me understand exactly how far away my partner is, and link speeds and some other details. And then finally, why is the initial RTT greater than the expected latency? So for that question, we're going to go back to the bounce chart again. And we're just going to note that because we have this extra set of round trips between the two steelheads, notice that it delays the return of the SYN back to the client. So we've just seen some kind of strange decodes in Wireshark that it's like, okay, what is this stuff? Why are we seeing a duplicate ACK? Why are we seeing these funny flags? Why are we seeing the high round trip time? And the high round trip time is because of this extra interaction between the two steelheads before we return the SYN back to the client. And you can kind of see that in the picture. So let's now take a look at our journey, the journey of the SYN ACK. So we're going to switch direction now. We saw what happened going from client to server. Now let's see what happens going from the server back to the client. And we're going to start with the first of 2 SYN ACKs that came from WAN 0 interface of the server side steelhead. So the let's see if I can get that to work again. There we go. So if we zoom into the TCP options, basically what WAN 0 is sending back to the steelhead, that the original client steelhead is saying, hey, I have received your query, and I'm on my way to see if there's other steelheads in the path. So this is just an informational to the client side steelhead. Hey, I'm here, I'm probing the path, I'll get back to you in a minute. So that's what this first SYN ACK is about. And then if we look at, okay, well, what did the web server send back on the LAN interface of server steelhead? So all the things you might expect, hey, 1460 segment size, SAC permitted. Here's my timestamp. Since the SYN had a timestamp option, the web server is obligated to, if it supports timestamps, to put its timestamp value in the SYN ACK. And oh, by the way, I'd like to do window scaling at level with a factor of 7. Now, then the server-side steelhead on the WAN interface, notice, does something a bit different. So now at this point, he's sending back in the SYN ACK, going back towards the client-side steelhead, hey, I'm your server steelhead. I'm closest to the server. Here's my IP address. Here's the port that we should set up our control connections on, 7800. And notice there's no other options that are being presented back to the client steelhead. And that's because these two steelheads are going to talk to each other with optimized algorithms and techniques. So continuing along the path, again, from the WAN 0 interface of client steelhead, and then the interesting thing about, let's see what the SYN ACK looks like going back to the client, And notice the timestamps are not there. SAC permitted is there. Segment size is what you'd expect. And window scaling, again, has been dropped down because the client steelhead knows that I'm locally attached to the client. So I don't need that bigger window scaling size. So that's the SYNAC journey. And there's probably a couple of more questions. So I mean, because I had these questions. Why are there two SYNACs on the WAN interface capture? We've talked about that. The first one is a probe response saying, hey, I got your probe. I'm continuing to probe the path. I'll be back to you in a minute. And then why did the server steelhead change the server scaling factor? And that's because at the client, that question just say at the client. And that's because the client is LAN attached to the client side steelhead. So we've just finished discovery. Discovery's complete. Now let's focus in on creating the connection pool for the inner channel so that there are some pre-built connections that are available between the two steelheads, just in case the client says, I want to open more connections. We don't really have to do that now across the WAN if we have a connection pool created between the two steelheads, which is a form of optimizing latency, because now we don't pay the penalty. Once these are set up, we no longer pay a penalty for opening new connections from this client to this server, which for a web browser transaction, there would be a lot of connections open. So let's look at the connection pool now. So here we're looking at the WAN capture on, and it wouldn't matter which side, we're looking at the client side steelhead. And notice that there's a bunch of 7800 connections that have been opened. There's actually 28, according to my count. And so these have been set up, they're in place, and now we know what they're for. They're part of the connection pool that was created after discovery. So we've talked about overriding TCP options. We've seen what that looks like. We've talked about the connection pooling concept between the two steelheads. We've seen what that looks like. So now let's look a little bit closer at ACK spoofing, TCP ACK spoofing. So in this particular connection, and I'm going to zoom in a little bit again. In this particular connection, notice that the initial round trip time is recorded as 402 milliseconds. So that's our kind of stake in the ground that says, hey, between this client and this server, when we did the connection setup, there was 402 milliseconds of latency, of round trip time. Now, some of that could be congestion, some of that could be other issues, like in this particular case, it's lab virtualization unintended consequences, because it really, we know there's 95 milliseconds configured on the WAN generator, or simulator rather, but the total time to actually complete the setup was 402 milliseconds. So let's take a look at our round trip times, round trip time to ACK, for example. We're looking at the gets /, which is packet number 11. And then notice that the ACK for that is in packet number 12. And we have sub-millisecond response time. It's like 21 microseconds. So you can see the round trip time to ACK. We're ACKing packet 11, and we did that super quick. Now, notice that who is sending the ACK? The server side, the server is sending the ACK. Now, it's actually being sent by the client steelhead on behalf of the server. So this ACK comes back quicker, which stimulates the client, if I can say that, stimulates the client to say, okay, well, let's keep let's send some more, your request was received. If you have more data, now's the time to send it. Like in the case of a post where, or sorry, an HTTP continue, where now the client may want to send more of the request payload. And then we have another example. In this case, it's the get icons blank request, which is in packet number 14. And then the ACK for that is in packet number 15. Again, it's being sent by the server, the server in the data center, but in reality, it's being sent by the client steelhead. And we can infer that because there's no way that the server in the data center could possibly get an ACK back that quickly. So that's our look at ACK spoofing. And now we're going to move into, that's it for scenario 1. And now we're going to move into scenario 2, which is using steelhead technology on my laptop with a steelhead in the cloud called SAS Accelerator. And that steelhead in the cloud is specifically set up to accelerate traffic, to put a steelhead close to certain SaaS applications like Office 365, Salesforce Box, etc., ServiceNow. And then with steelhead running on our endpoint laptops with a version called Client Accelerator, we can now set up optimized connections between our endpoints and SaaS applications. So in scenario 2, I've got Client Accelerator on my laptop in Orlando. SAS Accelerator is provisioned specifically for the Riverbed tenant in Office 365 Azure, which I believe is someplace on the West Coast, judging by the latency. And there are cloud steelheads running as part of something called a service cluster behind an Azure load balancer. And all of that gets set up as part of provisioning. You don't have to manage it. You don't have to maintain it. It's all part of the service for SAS Accelerator. But at the end of the day, there are versions of steelheads in the cloud. So we have our test plan. There's a test script that was planned out in advance. We're basically going to take a PowerPoint deck, create multiple instances of that deck with different names, and we're going to move that from my desktop on my laptop to my OneDrive on my laptop, which would trigger synchronization up to the cloud. I did before and after test runs. I grabbed packet captures, and I also did some screen video captures of the actual test so I could use the timing of what does it look like from the user perspective. In terms of the actions during the test, we copy from desktop into OneDrive using File Explorer, and then watching how long does it take to synchronize my local OneDrive with my cloud OneDrive. So that represents an upload to the cloud. Then another way of doing the upload is drag and drop from my, it says OneDrive here. What it should say is from my desktop to a browser view of my OneDrive in the cloud. And what's interesting about that copy is first we upload it, and that takes a certain amount of time. And then because the cloud OneDrive is synchronized with my laptop, we now need to download it to my laptop so that that file is synchronized with my local OneDrive on my laptop. Then some various other activities like editing the PowerPoint on my OneDrive, like duplicating a slide, and then seeing how long does it take to then synchronize back up to the cloud. Likewise, using SharePoint Online or PowerPoint Online to do that same type of edit on a different instance of the file, and then watch how long does it take to synchronize to come back down, capturing packets for all the steps. So the goal of all of this activity was to demonstrate time savings And the reason there's different file names is because I wanted to show that caching is based on byte patterns, not on file names. So these are not file objects caching. This is byte pattern caching, which is more efficient and more flexible. Because what you're going to see with one version of the cache, I can edit with PowerPoint on the cloud. I can edit with PowerPoint locally. I can do drag and drop from File Explorer. I can do drag and drop through a browser, and it's all using the same cache content, which is actually pretty interesting. And then taking a measure of the time savings. So I built my little test script in advance. I've learned over the years that you have to, at least I do, I have to plan out my test. Otherwise I get started on the test and it goes sideways. So this is my checklist of what to do, doing a ping in between certain certain steps. So I've got some ping traffic as markers in the capture files as well. So let's take a look at the first test, which is WAN OPT Disabled. So I basically turned off Client Accelerator on my laptop. And our topology looks like this. I've got my home office. With my internet provider, I've got 11 meg upload, 100 meg download. At the time of the test, I was using a 2.4 gigahertz Wi-Fi SSID, and I was capturing, in this case, I'm capturing from my Wi-Fi interface. I can't do TCP dump from Client Accelerator because it's turned off. So I'm doing the capture from the Wi-Fi interface. So in looking at, and I want to zoom into this, we're going to look at the evidence of what is the real round trip time when there's not optimization. So let me zoom into this a bit. Okay, so we're going to take a look at, we're going to focus on, well, I didn't make the frame names complete. Sorry about that. We're going to focus on this first segment, ACK, where that the rightmost arrow is. I wonder if I can highlight that. Can I highlight that with this? We're going to start with this arrow right here. And notice that it's an ACK from the laptop. So the laptop, my 192.168 address, the laptop is saying, hey, I got your data and I'm ready now for the segment that starts at stream byte 7537. And now the server is going to, once it gets that ACK, it's going to then send down that payload. The stream byte starting at 7537. And if you notice the delta time here between the ACK, if I can get this back here, come on. Yeah, if you notice the delta time between the ACK and when the data arrives is 498 milliseconds. So almost a half a second for the ACK to get back up to the cloud on the West Coast, and for the payload to arrive back at my laptop. So here's an example, and there's tons of examples in this capture. I just picked one out, one because we're going to run out of time here shortly, and it illustrates what happens with the high latency between me and Orlando and my cloud OneDrive, which is somewhere on the West Coast, probably Seattle, or somewhere in the state of Washington. So 498 milliseconds round trip time to ACK. It's a key measure. And again, there's lots of evidence like that. So the next thing I want to look at, again, this is a not optimized capture, or test rather. So uploading that 56 meg file from my local OneDrive up to the cloud. So there's another cost though, and this kind of gets back to my point about, does TCP pay a price for round trip time? And here we're looking at a bunch of retransmissions that are all clustered together, a lot of duplicate ACKs and retransmissions. And there's a cost to these retransmissions in terms of the throttling effect. And I don't have pointers in here about which packet refers to which, but I went through here and what I found in just this one screenshot is about 350 milliseconds of delay just dealing with this one lost packet. And that's because it takes time for one end to tell the other end, hey, I'm missing something, because we have to have that round trip time to inform the other end that, hey, I'm missing something. So there's a round trip time delay, not only with real payload, but also with dealing with retransmission control. So now what I want to do is let's turn on optimization, and we'll run the script again with optimization turned on and see how things look. And we've got about roughly 10 minutes or so to wrap this up so that we can get to Q&A. So here we are, I'm in my home office going through the cloud, but now I've got Client Accelerator turned on and I'm peering with steelheads that are in Azure. And now we've got an optimized connection between my laptop and some steelhead technology in Azure so that we can optimize those connections. So here's what we're going to see. We want to be on the lookout as we get into these captures. We're going to see some phantom TCP connections. We'll talk about that. We're going to look at some RTT timing, and we're going to look at data coming from a nearby cache and the fact that there's no retransmissions and faster times. So the first thing that threw me off, and it was quite a throw off, is when I looked at the LAN capture, there's these connections in there that didn't really make sense. I didn't know what they were. It's like these 6,300 ports. It's like, what in the heck is that? Where did that come from? What is that doing? So the first thing that I found is these ports, this traffic it never leaves the laptop. It's internal part of WAN OPT processing that leaked into the capture. And if you look closer, like I sorted by bytes, if you look closer, you'll notice that these are kind of paired. It's like, oh, hey, these two moved 150 meg, these two moved 116 meg, these two, it's like, hey, wow, these look like they must be related. And it turns out they are. So in order to really analyze this capture, the first thing we have to do is get rid of these extraneous 6,300 ports, which is really easy to do. So basically a display filter with TCP port 443, and then creating a new capture file using export selected packets. And now I've got a new PCAP with 443 only. You can see the name of it there. So now that we're looking at a cleaned up capture, let's take a look at the client hello handshake as an example of how long does it take, round trip time. Have we improved round trip time? So here we have a client hello that's happening. Let me zoom in on that. We have a client hello. Big packet number 58.226.24, immediately followed by a server hello, and you can see that in this ACK right here. We're ACKing 2624, and we're doing it in 15 milliseconds. So we know that the initial round trip time for setup was, in this capture here, 89 milliseconds, and yet we're able to get the server to ACK the client hello within 15 milliseconds. So that's telling us that we're actually serving that from a local cache. We're not serving that having to go all the way to the server, all the way back. We're actually serving that server hello from my laptop, from Client Accelerator on my laptop. And for SSL traffic, what's happening is my laptop is SSL terminating for the client, and then we're going optimized across to the cloud steelhead, and then we're getting back into SSL to hand off to Office 365. So if we look at another example real quick. Okay. If we look at another example, in this case, we're looking at payload coming, ACK going out, and then the next segment arriving. So it's similar to what we looked at in one of the earlier examples. We've got an ACK saying, "Hey, I'm ready for stream bytes at this point, 4065," and then what comes next from the server? Oh yeah, it's 4065. How long did that take? That took less than a millisecond. So we know that that's being served from a local cache. And one last feature slide, and then we're almost done, and we can get into Q&A. When we talk about cache from a steelhead perspective, there's some patented technology called scalable data reference. It's actually, you know, I don't know all of the technical details about it, but it's very, very effective. And it enables the two steelheads to synchronize their cache. And in the server side where the data is being served out, it's able to signal to the client, hey, start to serve out content from your cache at particular addresses and hash points. And it's able to do that very, very effectively. And we saw an example of that where it came out like within 0 milliseconds, the next segment showed up to the client. So very important piece of WAN optimization technology is caching, and this one is a special one. So last item, there's no retransmissions in this optimized connection. So if you think about, I'm at home, I'm doing this test, I've got Wi-Fi on 2.4 gigahertz. I honestly don't know what the other family members were doing at the time, but I know that I was not the only user of Wi-Fi at the time. So regardless of that, we still were able to do this test with no retransmissions. So not only did we get the benefit of ACK spoofing and the benefit of local caching, and one of the side benefits is no retransmissions, no retransmit timeouts, no fast retransmissions, no duplicate ACKs. The sender and the receiver don't ever believe there's anything wrong with the network that we need to throttle back. So this is actually a good thing. No retransmissions. And then the last slide, in terms of this testing that I did testing on 2 different days. And what was interesting, on the second day, like 30 hours later, I ran some of the initial scripted tests again following the script. And apparently the cache was still warm, not only on my laptop, but also in the cloud. And when I look back at the video captures of the speed, what we went from 64 seconds to upload this file, and then that's with a cold cache, no cache, to 16 seconds. The next day, it was still in the cache. Pretty awesome. And then downloading was 9 seconds versus 24 seconds. So there's some real user productivity savings with this technology. But to recap, you do need to expect that your captures are going to look unusual if WAN optimization is in the path. We looked at some examples of that. The testing that I did was very conclusive that with not only with branch steelheads, but also running in my laptop, talking to a cloud version, that for me working at home, the productivities are really significant. And it gets rid of latency, gets rid of retransmissions, and all my typical home Wi-Fi issues of not enough bandwidth, or my ring cameras going off and dropping my connection. None of that's important, or none of that impacts me when I've got this turned on. So quick summary slide of what the different WAN op features are. We talked about many of these. And before we get into Q&A, I just want to please ask you to take a moment to complete the session feedback form. I not only for today, but if you're viewing this on demand, I believe this form will still be available. So please give it a try, even if you're doing on demand. So that's it. Thank you very much for your time and attention. I know this is a little bit of an esoteric topic, but again, it's a review of some very strange conditions that when you see them for the first time in Wireshark, they could be very confusing. And I wanted to just help explain what those conditions are.